Good morning, all of you. So, as previously discussed, as a deterministic and random vibration, when an external excitation force is known to you, it is called a deterministic. And if it is unknown to you, it is called the random vibration. So, wind vibration of that wings of that aeroplane, that we can consider as a random vibration. Or uneven surface on that road, that uneven surface offers some external excitation force to that wheel of that particular body, considered as a random vibration, which is unknown to you. So deterministic and random vibration. Another one is the longitudinal transverse and torsional vibration. So according to that motion of that particular oscillator, motion of that particular body with respect to axis, with respect to the axis, that are again classified as a longitudinal, transverse and torsional vibration. So in longitudinal vibration, the mass moves up and down, which is parallel to the spindle axis. Mass move up and down, which is parallel to the spindle axis. Such type is called as a longitudinal vibration. In transverse vibration, that mass move, which is perpendicular to that axis of that particular shaft. Mass move perpendicular to that axis of that particular shaft, which is called as a transverse vibration. And in torsional vibration, that particular mass is moved. With some angle. That particular mass move with some angle theta, with respect to that axis of that particular spindle or shaft. So that angle of twist theta, provided in this case, and then that system is released. Suppose this case is move or rotate, which is fixed to this shaft, and this shaft is again fixed to a one support. Suppose this disc is twisted or rotated through angle theta, which is nothing but a twist angle, and then this disc is released. And when this disc is released, this disc oscillates about this axis. Of spindle or axis of shaft. In this case is nothing but a torsional vibration. So these vibrations are classified according to the motion of that particular mass with respect to the axis of particular spindle or shaft. Longitudinal, transverse and torsional vibrations. In longitudinal, up and down motion, which is parallel to that shaft, when that oscillator motion is perpendicular to that particular axis, it is called transverse vibration, and when it is twisted or when it is rotated around this axis, it is called the torsional vibration. So another case we here introduce as a transient vibration. So in this transient term we discussed in the next topics as in force vibration. This transient vibration, if suppose this pendulum is vibrating, this pendulum is disturbed from its equilibrium position, and that pendulum get oscillate about certain equilibrium position. Or suppose one beam is vibrating, one fixed cantilever beam is vibrating by providing some external excitation force at its free end. When you plot that particular amplitude versus time curve, or displacement versus time curve, in that case that amplitude is vanished after certain time. So if that amplitude is vanished after certain time or within a short time, that particular type of vibration is called as a transient vibration. That type of vibration we studied detail in the topic of the force vibration. So in transient vibration, that amplitude of particular vibration is reduced and get vanished after certain time, which is called as a transient vibration. Another one is the periodic and harmonic motion. Another one is periodic and harmonic motion. So that periodic, suppose that oscillative motion repeat itself after some equal interval of time. It is known as the periodic motion. And harmonic motion is represented in circular sine or cosine function. Harmonic motion is represented in circular sine and cosine function. So periodic and unperiodic. It means periodic, that motion which repeats itself after equal interval time is called as periodic. If it is not repeated after some equal interval time, it is an unperiodic nature. So these type of vibrations. So we go through these different types of the vibrations. Generally we observe in concern with these types of vibration. Generally I observed in concern with the type of vibration. So here we discuss the major types of vibration. In this topic. Now, as we discussed different types of vibrations, different types of damping, previously we again derived that equation of motion for a particular system by means of 4 methods, as a Newton's second law of motion, or energy method, or Rayleigh method, or D'Alembert's principle, or it is also called as the equilibrium method. So we already derived this equation of motion for a particular system for free vibration. Free vibration, it means excitation force is provided only once during the disturbance of that particular system from equilibrium position. So that free vibration, we write equation of motion as a mx double dot plus ax dot plus kx is equal to 0. So equation of motion for particular system, pre-damped system we consider as a, or we derive as a mx double dot plus ax dot plus kx is equal to 0. So here again x is nothing but a displacement of that particular vibratory body. X dot is nothing but a velocity of that particular body. X double dot is the acceleration of that particular body, or acceleration of that particular mass. So again, if we look at this equation of motion, this is a second order differential equation. So we derive equation of motion. For a particular vibratory body, and we write this as a mx double dot plus x dot plus kx is equal to 0. Now it is a second order differential equation, and we are interested to find out solution of this equation. So solution of this equation is nothing but a x value or x dot value or x double dot value. Solution of this equation is nothing but a that parameter, by which parameter we can express that particular motion of that particular body. Either displacement, either velocity, or either acceleration. By any of these 3 parameters, we can express that motion of that particular body. So we are interested to find out solution. So find out solution is nothing but a find out x or x dot or x double dot. So here we go through this, or we are interested to find out the solution of that free damped system, solution of that equation of free damped system. So we write down equation of motion here. Now this is the second order differential equation. So for second order differential equation, there are two roots. For the second order differential equation, there is a 2 roots, and that roots having 4 cases. This system having second order differential equation. Having 2 roots for this equation. Now 2 roots may be, again there are 4 combinations. These 2 roots may be equal, may be unequal. These 2 roots may be equal, may be unequal, and these two roots may be real one or may be imaginary one. So these two roots may be real one or may be imaginary one. And in again for this real roots, again there are two cases. Maybe these roots are real equal, real unequal, or in imaginary case maybe these two roots are the imaginary equal, imaginary unequal. There are four possibilities. There are four possibilities of these roots of this particular equation. So we go further and we discuss about that, which possibility we can consider. Now to solve this differential equation, solution of this equation, we go through that mathematical subject M3, mathematical subject M3. We already go through the differential solution of the differential equation, and that solution of the differential equation is nothing but x is equal to a1 e raised to u1t plus a2 e raised to u2t. Solution of the differential equation, we know that solution of differential equation as a x is equal to a1 e raised to u1t plus a2 e raised to u2t. Now a1 a2 are the constant and u1 u2 are the roots of this particular equation. u1 u2 are the roots of this particular equation. Now our task is to find out the roots of that particular equation u1 and u2. That roots of particular equation which are denoted by u1 and u2. Now to find out these roots u1 and u2, we assume that solution in the form of x is equal to e raised to ut. We assume that solution in form of x is equal to e raised to ut. Now we put this x is equal to e raised to ut in this differential equation. In this differential equation, mx double dot plus cx dot plus kx. While putting this x is equal to e raised to ut in that particular differential equation, that particular differential equation now transformed to a quadratic equation. That particular differential equation is transformed to a quadratic equation which appear like this in terms of quadratic equation of u square plus u plus constant is equal to 0. U square plus u plus constant is equal to 0. Now that differential equation is now transferred to a particular quadratic equation, and now for quadratic equation we can simplify this quadratic equation and we will get two roots. For this quadratic equation like this. Two roots for this quadratic equation like this. Minus b plus minus square root of b square minus 4ac divided by 2a. So we can obtain this two roots of this particular equation, and that are nothing but a u1 and u2 value, and that we put into the solution of that particular system. So these are these are the two roots. U is equal to minus c by 2m plus square root of c square by 2m square minus k by m, and another one is a minus c by 2m minus square root of c square by 2m square minus k by m. These are the two roots. Now these two roots we put into the solution of this particular system, equation of motion of particular system. X is equal to a1 e raised to u1t and a2 e raised to u2t. a1 a2 are the constant, u1 u2 are the roots, and that t is the time, particular time at which we have to find out this displacement x. And this task we have to find out the roots of that particular equation u1 and u2. Now we already find out that u1 u2 like that. u1 is this one, u2 is this one, and we put that particular u1 here, u2 here, and we will get solution of that particular equation of motion. Nothing but a displacement. Here this x is represented as a displacement of that particular body, oscillatory body at a particular time t. Displacement of that body x at particular time t, and this is nothing but again we can